to the new subject or the new course in this semester, embedded systems. So by this first lecture, we will make a short introduction to the embedded system. We will see what it is about, and mostly we will discuss about from what is made an embedded system. So few words about me. My name is Andrei Bragorenko. Most probably you already heard about me because of the my voluntary activities in Engineering Club by Krala, but my main activity in the university is having the course. I'm a lecturer, by the way. So during more than 20, for about 19 years, from the moment I involved in the university, I let's say teached many courses, and we see here the whole list. It's programming in electronics. Mainly, it's related somehow to Arduino programming for the starting courses in the second year of the microelectronics. I also got some lectures for the microprocessor and interfaces, meaning it's a kind of embedded system, but not really. It's only one part. Embedded systems in English, embedded system in Romanian, Internet of Things, the same cars more or less, but for the not software engineering in Romania, in the fourth year. And also I have some courses in hardware description language, HDL, and digital design. Okay, but all those courses, all this experience, usually when I initiate a new course, usually I have some experience from the industry and see that in industry the requirements regarding the embedded system is different that we have here in the university, and I try to bring the experience through the courses I have in the university. So my experience related to the topics that I teach in the university are coming from the first of all from the design verification. Even I started or I learned to program on C, let's say, but my first programming language or first language for first computer language was HDL or Verilog HDL. That is a hardware discrete language in which we can write some code, and after not compiling, after synthesis, this code became a circuit, a digital circuit. Okay, so after that I was involved sometimes in digital design and verification, and after designing some tools for, let's say, EDA, and design automation. Okay, let's say tool that was used to check the error and during the design of an integrated circuit in silicon. Okay, but the most related experience to the embedded system was from the moment I started to work on automotive via the Arop software company. I was working for a department of hybrid electrical vehicles. I was working for ADAS. I also working for the AutoSAR. This is more an engineering center that was developing some components for an open system automotive architecture. Yeah, and in parallel, as I told you, I have some voluntary activities that where I involve students in extracurricular activities because only the theory will not make from you real engineers. You need to practice somewhere, and you need some challenges and something that you don't have to get a mark. You have to get some experience. So in this case, we have some let's say awareness events like practice session, master classes, or engineering talks. Also, we have a few boot camps in a year. Mainly, we have free the autonomous driving robot factory, by the way, that will start in March, and you are invited. I will say you the. I will describe you the offer for that. The PCB design is more or less related to electronics and Internet of Things bootcamp. That is summer camp that usually for about, I don't know, it's about 7 years we already have this bootcamp every year. Okay, and we try and validate our experience competing with other teams. In this case, we have some competition. Here in the engineering club, we accept students for diploma projects. And of course, we have some project that is, let's say, have some impact in our local engineering and embedded systems. My education, of course, who is related. I finished the microelectronics here in Technical University of Moldova. I got 2 masters, one master's degree, one here, one in Romania. And also, I started my PhD starting in the microelectronics, but I changed it recently to the somehow software engineering, but also related to the embedded systems. So now, I think this year I will finish it. But let's see what is an embedded systems. So when we are speaking about an embedded systems, we can say that is okay. We have some Wikipedia definitions. Maybe you can find it also. But okay, let's see. Somebody.
Sorry, question.
But why you didn't tell me?
I told you. I just
in the voice. Chat. Okay, so let's continue differently. I will start to share, and we'll continue. Okay. So let's start. What is an embedded system? An embedded system, usually you can see here some pictures. Okay, you can find a lot of definitions, but from my point of view, if we'll speak in some simple terms, it is some things. Okay, everything. Okay, it can be, it could be, let's say, anything you want. It can be, let's say, this cup or this table, yeah, or everything you want, a real thing. We are not speaking about devices, yeah, where we embed some, let's say, just a second, where we embed some processing power. And this processing power, meaning a microprocessor or microcontroller, this processing power allow us to make this thing smart. So we embed the smartness here in one thing. In everything you want, you can just add some processing power, and you start to do smart things with that. What that means? Let's say this cup. This cup can have some sensors, and it can, let's say, color your cup in one color that will indicate how hot is the water or how cold is the content of this cup, let's say. And in this case, it will not be anymore just a cup. That will be an embedded systems, or a smart thing. So this is the approach that I follow when I try to explain what an embedded system is. And usually we see here an embedded system that see, okay, we embed here some things in a box. Okay, this box started to be an embedded system. Most probably this is more or less looks like a computer or an industrial computer. Another thing that you can imagine how an embedded system look like is the explode picture of some device. So here we see some ECU. ECU comes from electrical component unit, electrical control unit, and we see that this box has inside some electronics, so it started to be an electronics. Most probably it's used to control something. It's part of another bigger things, but it's how it looks like. So how to detect if it is an embedded system or not? Just see, is there any microcontroller or processor inside or not? So applications. What kind of application could be qualified as embedded systems? Okay, an embedded system usually now we can meet on every house. Okay, on every house we can see some smart devices that working together make the home or the house to be smart. But the smartness of the house is not having those things together. Yeah? The smartness of the house is when we are embedding those things and define some features of the house. Okay, the smart house doesn't mean that we have smart things inside of it. The smart house means that the house can solve some problem using the processing power or the embedded processing power in it. So in this case, the smart house or the smart home will feel us. Yeah, when we are entering, it will close for us the house because the house or the home will recognize that we are the owner of the home. Okay, when we will enter the home, I don't mean that okay the bulb will switch on. The home will decide to light the room. Okay, the home will decide that we need some to change some the temperature, the environment temperature. The home will decide that I need some relaxing music because I'm coming from my job and I'm very exhausted, so I need some relaxing. Yeah. So as a system, that means that home has some embedded processing power or embedded smartness inside of it. Okay, in this case, we have some smart devices that together form a complex system. And usually such systems are qualified as Internet of Things. That means in house we have a lot of devices, a lot of embedded devices that are interconnected via a network and form together an Internet of Things that as a system can be considered as a smart home. Combining, okay, now the term of Internet of Things means that when we have a lot of things, yeah, interconnected, we don't have let's say devices or we have electronics connected. We connect things. That means I connect this pen with my cup, yeah, with some furniture, with my table, yeah. But how it is done, okay, how the connection is done is the how it was, how, let's say, how electronics or the smartness was embedded in these things. This is what means to have an Internet of Things, an Internet of objects, okay, that are connected via some embedded power. Okay. Now, when we are speaking about the internet, of course, we see that Internet of Things now is exploding, yeah, because we see how big was the network in 1992, and see, yeah, by just for comparison, because this is, I don't know, maybe even this picture has already about 5 years or 10 years, because now the network is even more complex. We can say that it's just a part, or it is just a snapshot of many years ago. Yeah, but combining many smart homes, yeah, we are going to even higher level, because here we have some things interconnected via a local network, but now we are going to a higher level, or to the upper level. We are connecting homes, okay, some apartments, let's say, in one home and on one big house in a network. After that, going even wider, we have smart city. A smart city application, okay, when I'm speaking about the smart city application, what does it mean? That means that, let's say like this, the engineering that is developed now is everything is done to serve us as a humans, to have to concentrate to the most most important things, but everything that can be automated is automated. So let's say I'm waking up, the house is making me a coffee. Okay, it is waking me up. It is taking care that I take the good dress. Let's say like this. It's preparing me a coffee. It is, but now I want to go safe to my job, and in this case, first of all, the house will help me to go outside on the right time. It will call for me the elevator or the lift, let's say like this. Yeah, it will call for me the taxi. I will enter into the taxi. Taxi will be in the right time where I want to be, and it will even switch. It will switch on or off the traffic light in order to achieve the goal to be on time on my job, job, or let's say on the market, or I don't know where we are going. So in this case, the application is even wider. The application is is serving us is the smart city. More than it is serving, the application of the smart city is serving not only me, but also is serving all the people that is working on living in the smart city. Okay, this is, let's say, what means when we are scaling. Okay, we have one device, after that multiple device, we have a room, a house, a home, but everything is connected to the whole interconnected system, and all those microcontrollers are just the let's say the solution how to solve. It's not the target. Okay, I will buy an embedded system. No, I will buy a solution that is done by is made by one microcontroller, 10 microcontroller, 100 microcontroller, or I will connect to the smart city where we have millions of microcontrollers. Okay, same we can say about automotive. Yeah, if you remember, okay, we will go in the past. We'll see that first vehicles were without even engine. Yeah, it was tracked by a horse, but technology came, and now we see. Okay, the information from the 15, I think, years ago was when we were on the student competition. student contest. We had a presentation on 15 years ago. They told that this speech was 15 years ago. A modern car now has about 40 microcontrollers on board, but this information is 15 years ago. Now, thinking that everything is exponential. I don't know. It's about hundreds, many hundreds microcontrollers we can have on a board of on a car. Everything is connected. Every single piece of a modern car is connected to the internet. Yeah? Why? And okay, every single thing in the car communicate to each other. Okay, when I want to get out, it see that I try to get out. It inform the main computer or unlock or unlock the door if I need. Yeah, but it sense that I want to touch it even. Yeah. Now, environment monitoring. Okay, it's another embedded system application or Internet of Things application that has more and more importance in our daily life. Why? And most probably you already heard about the carbon footprint or carbon, I don't know how to say exactly, but let's imagine many years ago, let's say 50 years ago or even more, one apple, it was green, but not green by itself. Green means ecological, not by itself, but to produce it and to deliver it to me, even the process didn't pollute the environment. But now, even the and the apple that I buy, even it is completely ecological, but producing this apple or any vegetables, meaning we use, let's say, elementary, we are using a car to bring it to us. Okay, this car emit carbon in the environment, and that means the footprint of these vegetables or this apple is already not equal to zero. More than it, as many processing day by day, let's say, we have this processing chain is higher and higher and higher, and to control it, we need a kind of environment monitoring applications that are monitoring everything and see that this apple is really eco, because maybe it's eco for me as a consumer, but it's not eco regarding to the environment. Okay, to monitor it, we need a lot of systems from the planting until it is delivered to us. Okay, and now we need some, of course, solution to monitor, collect data, process, and so on. Automotive application, even automotive, I told that, okay, automotive itself, like a home, let's say, a home has many devices, okay, a car has many devices inside. A home can be scaled to a smart city or an Internet of Things. Vehicles, okay, we can make an Internet of Vehicles. Now, vehicles could connect each other and to negotiate which of them will pass first the cross, the intersection. Okay, but usually, let's say that we don't have technology. In this case, I will try, okay, not technology, but we will not have Internet of Vehicles. I'm running on high speed. Another car is running on high speed. It is my friend. I call, take a look. I want to cross the intersection. Please make a break. Okay, in this case, the Internet of Vehicle will do it for us. They will synchronize in order to not spend the time, yeah, on staying, but everything will be synchronized. More than it will synchronize with all the traffic lights, with all GPS and all the things. So this application now is a new trend that is, we are speaking about the Internet of Vehicles. Okay, of course, now, and it is related also to our country, intelligent agriculture application, or AgTech. Okay, what is the thing here? Okay, and now when we are speaking about the things and Internet of Things in agriculture, we should first define what is the thing. Okay, and in this case, we have this, let's say, plant. Yeah, and now we want to make it an embedded system. So we need to embed some intelligence in this plant. How we do that? We just include some servers, some sensors, some application, and so on, and convert it in a technological plant. So in this case, we are speaking, we are defining, we monitoring, and we even, let's say, we are doing a kind of smart farming. And this itself, okay, let's imagine we automated everything. I want a plum, or I want some vegetables. It will provide me somehow with some technology chains. I don't know how, but in this case, with some vegetables will come from here to my house using technologies. This is about the, let's say, intelligent agriculture applications. Of course, we have industrial applications, and the let's say the highest level of the application. Let's say I want you just chat with the IoT or industrial IoT. I want and define your product with some script, and the manufacturer will, or the plant will, the plant will produce it according to your specification, without intervention of any human. You just order it or select the product of what you want. Okay, I want some product that is some combination between that. I want this part from here, and the plant will produce it for you. Okay, and the industry, when we are thinking about the industrial Internet of Things, it's not only the, let's say, robotic arm or something like that. It is connected even with supplier chain. It is ordering for itself the materia prima. Materials and so on, in order to achieve the goal, to serve us. Yeah. Oh, okay. So shipping, business, accounting, everything is connected in the an application of the industrial Internet of Things. But let's start then some theory. When we are speaking about the Internet of Things, okay, for me, Internet of Things is a scaled embedded system. My approach is something somehow different. I'm going to the system from top down. Every time I'm thinking about something, I try to imagine the whole. After that, go inside. So now, by the way, let's make some exercise to see if you are here. Yeah, by the way, I have a question. Embedded system versus Internet of Things. I did some explanation, okay? For me, Internet of Things is a scaled embedded system, because Internet of Things usually, let's say, an embedded system, it is a thing, yeah, where we embed some, let's say, intelligence. After that, when we are connect things together, this means an Internet of Things. So we cannot speak about the Internet of Things without speaking about the embedded systems, and more than it, when we are connecting many embedded systems together, we have an Internet of Things. This is let's say, connection between Internet of Things. Alexandro, did I answer you? Okay, then. Please just tell me from 0 to 5 in the chat the level of understanding the, let's say, the proposal of the unembedded system. Just to check if you hear me. Okay, then let's go further. So, IT as a system, let's see how we can explain it in detail. Let's say everything you imagine that is serving you, or everything about the as a solution, usually you can say that, okay, it is a system, it is a whole. And usually a system is, let me put a smart. Okay. When we have a system as a whole, we say that, okay, it is collecting some data from outside and providing some results. Okay, but we can say differently. Okay, a system as a whole, it's made from, it's a collection of components that are interconnecting together in order to obtain the results. Yeah. Okay, now thinking about the system that is from the structural point of view, we have components and interconnection between them. From the point of view, or from the functional point of view, it is collecting data, processing it in order to provide the result. But it has a complex function that can be split in many functions, more than it. Any or part of functionality can be associated structurally with a subcomponent. Yeah? And in this case, we can say that, okay, we are going deeper inside and see that a collection of components with its own transfer function, okay, and connecting some things between them, we have another layer of the granularity. Yeah. So now, let's say like this. We can say that this one we can go to define as a system, as a subsystem, and go deeper inside, and so on and so on. Now we are making abstraction about the it is hard or soft or heavy. We are speaking about the system as a whole and about the whole functionality. Now we are when we split the functionality in parts, okay, we can go and do it again. And we are going to the functionality that we can control. More than it, we can associate the functionality that is on same as functionality, the main function or the whole function is related to the whole system. Here we have the structure. Here we have the function. Yeah. Okay, now looking to the Internet of Things, yeah, we can say that Internet of Things, or let's say smart home, smart city. Smart home. Okay, a smart home by the way, when you're looking to the smart home, we have some inputs from us, let's say, as a user, and it's provided some output. Let's say that it's heating the room. But in order to provide the smart home function, it is using many devices. 1, 2, let's say, smart TV, heater, I don't know, any other devices. But we can say, as a whole, let's imagine that the smart home is just one electronic piece that usually that in order to have it apart, we just cut it in parts and put it one side of the room. This is another side of the room. This is another side of the room. This is another side of the room. Let's say we have a TV, yeah, and I want to have this TV three-dimensional, meaning I will make it like this, yeah, and I have 2 TV, but we'll have the same monitor. By the way, most probably you seen on the conference when we have 2 TVs, but the image is or some things are sliding from one TV to another. Let's say this TV was just split in 2, and the connection between them, okay, are restored by the internet. So, as a theory, we can say that a system, yeah, a whole system can be splitted in Internet of Things, because a system is split in components, and when it physically are going apart, we have many devices, and the connection usually as a whole, when we are cutting it apart, the signals are transferred not directly by a wires, but we need some, let's say, Wi-Fi router, or even 3G or LoRaWAN, or I don't know. Yeah, and this is how we granulate and how we make things smart. Okay, we don't have a single device, but we split it in parts and distribute in a room. Okay, now one device. Okay, one device, and let's take it apart and see what is the structure of one device. And you remember that one function, we say that one function is split in many functions. So now what we can say? Structurally, we say that, okay, a system as a whole is a collection of components that are solving together some, let's say, the problem. Yeah. Now, we can say that the components or functionalities that are related to the data acquisition are combined together in the sensing components. The functionalities that is acting to the environment are collecting together in the actuator component. But let's say we are not speaking here about the domain in which it is implemented. Okay, we are speaking on the just I want to bring information from outside, from the PI, from physical environment, as information here. How? Okay, the component. Now, every component from here, okay, we have here power management, user interaction, even communication. Now, every component, let's say sensor, yeah, it has some implementation in mechanical engineering. Some parts, okay, the shape itself, the construction, how they interact with the environment, okay, it has a physical shape. After that, we have some electronics made by electrical engineering. Yeah, that we have some signals, and it's connected to the microcontroller. Okay, microcontroller, by the way, also is a part of electrical engineering. And now, in the end, we have some software engineering. Okay, we have software engineering here. And now this, let's say, is the component sensor, and the component sensor is made in different domain, let's say, part of the components, and we can say, okay, we can go inside and split this big system component and many domains component, let's say mechanical part, electrical part, and software part. Okay, and now during this course, we'll go through all the, so this, by the way, this diagram is, let's say, the all the subject we will have. We'll have one chapter for the, let's say, for the user interaction, one chapter about the operating system, one chapter about the sensing, one chapter about the actuator, communication, of course, databases, or how to process information, how to store. Okay, it is not exactly related because, okay, we have variables, we have some files and so on. This is more covered by other topics or other courses, but the main components that are consisting of this, those components are, let's say, auxiliary. Okay, and the power management also, okay, we are not covering it here. It's more hardware related. But this one, this one, this one, okay, and others, and somehow Internet of Things. Yeah, when we are connecting together, we are covering in this system. So what are the chapters? Chapters is user interaction. User interaction is a collection of sensors and actuators that are specially designed to interact with this kind of human-machine interface, HMI. Yeah, we can have different kind of interfaces, and we'll see that on specific topic when we'll have on the special cars. Okay, operating system. We will see what is an operating system for embedded system, how we can do that, or we can even define with few lines of code and to develop a very small and light operating system. We will see that even continuous loop also can be qualified or classified as an operating system. We have another chapter is sensors. Okay, we will learn about how we collect information in order to transfer the pi to info. Okay, and we will see kind of what kind of sensor we have, how we classify them, how we transfer, what is the real process, how the physical changes in the environment are converted to the information, and what is the function chain. Of course, the diagnosis, we are following the changes here and detect some strange things, okay, or strange or some specific things, and we can qualify them and manage if that okay or not. Is that an error of the system, detect some internal error, detect some external malfunctions, and okay, we have we'll see another chapter after. We have the actuators. We will learn the way how the information from the software is converted to a movement, yeah, action. Okay, so next, protection. Let's say we detected by a diagnosis that is something is strange, something is not okay. We have to react somehow, and to protect the environment. Yeah, and the system itself to not break, let's say, the system and the environment. Okay, of course, we will discuss about the control. Let's say we want to control something. we want to control temperature, we want to control behavior, we want to control something. What that means control? To manage something, to do, to behave as we want. That means to control. That means we are monitoring it and make some actions. And we'll see that control means to collect data from outside and to decide how to act or how to adapt the action in order to be under control. Okay, and we will see some very simple as open loop control to the, let's say, fuzzy control. It's a kind of expert system, the simplest, let's say, we'll see. Okay, we will not speak about, of course, the now the machine learning and the other things that are out of the context of the embedded system. It's something special, and it's a higher level. Even for machine learning, even we don't have to think about the problems that are solved by an embedded system. But I think in our meeting we have some guys that already are doing machine learning. Maybe they help us, or even they can use the machine learning in PBL program that we'll have in parallel. Okay, communication. How we transfer information between devices. How the devices are communicating each other in order to build an network, an Internet of Things. Yeah, because okay, we have things. We have a big thing. Yeah, let's say this is a phone. Yeah, as physical. Yeah, this is the thing, phone or cup. And these cups have some engineering solution for sensing, actuating, user interaction, and so on. Yeah? And this cup should communicate with this cup or with this table, let's say. Yeah? And how to do that? And we'll start with, most probably already have some topics or subjects on the, for sure we have, but here we will point some things. What means to have, what communication means, okay? And by the way, can you write me the simplest definition of the communication? What the communication is? Please write down in the chat. Waiting. Okay, maybe we have a delay, but fast track. Please raise your hand who is still here, who is hearing me now. Okay, exchange. Oh, okay. Started to be okay. Yeah, I like it. A dialogue exchange of information. Okay, nice. Yeah, the communication is the process, let's say, of information exchange to transfer, let's say, information from one entity to another, but not exactly entity to one object. But the communication is even the communication itself is older than embedded system, because communication and the communication protocol has a longer story even than let's say electrical engineering or something like that. We'll speak about that after. Okay, thank you for interaction. Okay, communication between devices. Devices, I say, it's more than devices. It's not about the changing signals. It's the process of transferring information. This is the closest process of transferring information from one point to another. Is communication. Let's say I communicate with you, and I transfer information from my brain to your brain, and everything between us are just some are forming the communication channel. First of all, the communication channel start to be the air. After that, some technology. After that, another air. After that, your ears. Okay, after that is the brain. But we will speak about that in the communication. Okay, it's more philosophy, let's say like this. But we will go to the network communication networks, protocols. We'll see what and how it's related to it, because most probably you already please lower your hand, because I want to ask after another questions. Or let's say lower your hand. Okay. And cybersecurity. Okay, we will just touch cybersecurity because our course is more related to it's more related to how to build an embedded system. Okay, but the cybersecurity is a separate topic where we have to what is the subject of cybersecurity? Everything, every touch. Because when we are speaking about cybersecurity, it is protect the device against the humans. Yeah. There is another side about the safety. Safety when you are protecting humans from the device, and we will see that cybersecurity and safety is something similar but is different. Security. Safety when you are protecting humans against the device or against the object. Cybersecurity protect objects against the humans. Okay, but we will go through the architectural to define what means and what means an architecture. And usually it is referring to the structural view of the system, meaning that a system is made of different elements or components and relation between them. Yeah, and okay, but maybe there are some definition even on Wikipedia, but when we are speaking about the architecture, okay, usually we are thinking about we make a relation to the house architecture, yeah, or architecture of building. Why? Because taking this metaphor, okay, we can understand it better, because we should know everything. Where are things, let's say, or where are the elements of the system and how they interact. Okay, and architecture usually is related to the blocks and interfaces. The behavior itself, it's about behavior, yeah, or okay. Now in embedded systems, usually V model development process is used. By the way, does anyone heard about the V model of the development process? Just raise a hand. Okay, the V model process development process of embedded system, meaning that we have first requirement gathering. After that, we define specification. After that, we have requirements, means what should be, and specification what is, let's say like this. Yeah. After that, we have architectural design, yeah, the structure and interfaces, and detailed design means to have the behavior. Now, in the behavior, we have sequential diagram, flow chart, state machines, and so on. And after everything was detailed, let's say, yeah, the behavior was detailed, only after we go to the coding stage, because from this model, by the way, it's usually we are using UML for that. From the UML diagram, we have a lot of tools that are converting even better than us the model the codings. Of course, we have unitary test when we are checking the design. If not, then we are going back, and so on. So one iteration means to go, let's say we have a small sensor. We are going like this, integrate it, and check the system, and so on. Okay, when we're speaking about the system, let's make an example here. Yeah, the system. Where is my pointer? Okay, the system. Yeah, it's split in subcomponents and make some interaction. This is when we are speaking about the system as a structure. When we are speaking about the system as a function, we have a big complex function that is split in many functions. Okay, we have inputs and provide outputs. Now, going to the embedding level, and this most probably will explain you why we have embedded system, or what is the hierarchy of the embedding. First of all, we have the CPU, okay, but even going inside of CPU, we will have two parts. We will have the control part, yeah, or control state machine, or automat, let's say state machine, and executor state machine. Yeah, and now here we have some memory, I don't know, but here this loop is execution loop, and here we have the control loop interacting with two devices. Let's say one is for the execution of the program, another for evaluation, and some transfer commands. We can build a microcontroller. Okay, this is CPU. Yeah. When we want to build an MCU, we add some peripheral, and we have the MCU. Okay. Now, let's go. Let's embed it. Yeah. Okay. We embed a control loop and execution loop into to form a CPU, and in order to obtain an MCU, we embed a an CPU plus some peripheral. We have the MCU. Next level, yeah, okay, we have the CPU plus I/O, and we have microcontroller. We are here on this level. Let's go further. We can even embed more in the same chip. And now, most probably, if you will see uncover or unbox, let's say, destroy the phone, or will open the phone, we will see that we don't have more than single chip here, and some wires, some power elements that is are too big to be embedded in the same chip. And now, when we are using a microcontroller and some specific, let's say, MP3 encoder plus other things, we can say that we have a system, the whole system embedded in the same chip. Okay, the whole system embedded in the same chip. Let's imagine, if we look inside of the phone that was made 20 years ago, let's say Siemens C25. In this case, you can see clearly that I have a microcontroller, I have the radio channel, I have some drivers and so on. Yeah. In this case, our day phone is nothing except one chip and some wires. Yeah. Why? Because it's cheaper to make everything in one turn. Yeah. To add some, let's say, connections, LCD, and that's all. Yeah. And in this case, we have, let's say, a microcontroller, but more than a controller, a whole system that is integrated in the same chip. Yeah. And now, one of the examples for the microcontroller is let's say Raspberry Pi. By the way, just raise your hand who used ever to write some lines of code for Raspberry Pi. 2. I think more. Only 2. Okay, we will have a chance. You'll have a chance now for Internet of Things to use it. Because most probably you'll make some application that are not enough to use only an Arduino microcontroller. But we can say that we can have a whole computer on a single chip with memory, video card, and everything else. Okay, but let's say we can go now. We have an CPU. Okay, after that we have an MCU and system on chip. That means we have some electronic components plus microcontroller, and we have a system on chip. But the ECU is also a microcontroller plus electronic component. This means we can have an ECU that can be, let's say, integrated in a SoC, or it cannot. So in this case, ECU will look like this. We have here microcontroller and some components, memory, and so on, and everything is on a PCB board. Yeah, and in this case, the next level, let's say, is the level of embedded is okay, CPU, MCU, ECU, and the next level is device. Okay, and device, what is device? Device is the object itself where the everything was embedded or boxed. Okay, now when we are looking like this, yeah, going inside structurally, we see how the hardware is done. Yes, but this is only the physical shape of the physical domain of the system, or electrical domain, let's say, plus mechanical. But when we are looking into the device architecture, yeah, we can look even what is here. Yeah, because this is bird eye view or top view, and see that we have some sensor, actuators, and so on. But I would like to see what is here inside, and we will see that every component can be defined by a stack. Similar, by the way. Did you hear about the TCP/IP stack? Please just raise your hand. Nice. I seen 10. Okay, only 10 of you. Please raise your hand and keep until I will say, okay, it's enough. Okay, it's dummy counter. I see that. Okay, because, okay, only 10, because most probably you already have some courses related to the computer networks and communication, most probably. Okay, and this is the example that I use for defining the stack or to explain the stack, because we have the physical layer. Okay, we have the hardware, and we have the software. Okay, but hardware is done by electrical engineering and mechanical engineering, and we have here device. Okay, somewhere there is device, but the physical environment interact with the device. Device has inside some ECU, the ECU abstraction layer. After that, we have the MCU abstraction layer. Okay, the driver of the micro. We have a driver of the microcontroller. By the way, its name most probably already heard. Just raise your hand if you heard about Arduino.h. Yeah, and Arduino.h is microcontroller driver. I don't want to build that. I just take an Arduino and have the Arduino driver and so on. So now we have on ECU layer, let's say we have some sensors. Yeah? I buy from eBay some sensors, and of course I have support from libraries, also from Arduino libraries. Yeah? And until here, everything I can buy or can I download and so on. After that, I can build some my own services. So now, until here, we can say that we have embedded system platform. Because starting from here, upper, we have the application layer. Now on the application layer, we will have some features, let's say like this. Everything related to get, scan, read means to have the information from outside to, and everything I want to send somewhere, I have the information with function like set, write, print, write, send, and so on. I have to send information outside of the application. Application is somewhere here, and through those layers, I send information to the communication, to the sensing, from the sensing, okay, to the actuator, interact with human. Okay, now this is the approach that I tried to adapt to define what an embedded system platform is in order to separate the application from the platform. That means to have some cross-platform application, but we need to operate smart in order to not have plain code. We need to organize everything in layers. But this is not my idea or everyone's idea, because of course we already heard that we have already ISO, and seems that not only ISO, but let's say in automotive open system architecture, we have the same. We have application, and application usually are cross-platform, and most probably you heard about the runtime environment. Yeah, it's not about automotive, but what is runtime environment? It's a layer or an abstraction that I have the access to the system or to the platform. Yeah? And here we see that now automotive open system architecture, we have somewhere here the operating system, let's say Linux, Windows, or something else. And we have the driver of the microcontroller, driver of the many drivers, let's say, for the ECU abstraction layer, some service layer. Yeah. Now, when we are building application, we have some components, yeah, defined on the application layer. That means we have one component that is interacting with second, yeah, but everything is done by runtime environment. In the architecture, we are defining like this, but everything is going through the platform. Yes, we are going to the platform call. So now, in this way, we are defining some structure, but the platform itself as, okay, of course, let's say like this, in your application, do you define that you are using Windows? Okay, no, because you are defining application, you are working on the application layer. On the microcontroller, most probably you will need that. You will need to separate, because when you are working on Arduino, let's say, directly with the pins, that means you are working on the very low level, and when you want to port the application from one microcontroller to another, it will not be so easy. Yeah, but introducing some layering, yeah, you will build some application, get temperature and set the power. That's all. Now, of course, automotive open system architectures has some components they decided on those guys staying together. Let's say, okay, I want to buy from you a component. Okay, but I need to think about the interfaces and how to adapt interface. So they met once and say, let's define some rules how we define components and a common architecture for everyone in order to compete only on the applications. Yeah, and in case I define some memory abstraction or a memory stack, it should be compatible from one platform to another. Yeah, and those all are standardized and usually can be provided by one vendor or another. More than it, in this, let's say, environment, in the automotive environment, we already have some companies that are developing some small parts of the application in automotive. That means if before the AutoSAR only BMW only BMW is writing code for BMW. Now everyone can write for BMW. Everyone can code or send the quotation, let's say, to participate to a quotation to work for BMW. What we can write, or what kind of application we can write on BMW? Everything. Okay. Let's continue then. So let's have an example. Yeah, here we have, let's say, a sensor logger example. We have here the architecture. We have some components and interfaces, but looking on the layers, we will see that. Yeah, we will see the communication. We will see the sensing, and we will see user interaction. Yeah. Everything equal. And here is the application layer. Okay, this one that we are seeing on the top is defined here. Okay, this one is defined here. Okay, now another application. We have the application, we have this one. Yeah. Everything is defined by stack, angle stack sensor, stack of the angle sensor, and so on. So going to this is the let's say architectural example when we are speaking about the structure of architecture. When we are speaking about the system or functionality of the system, we have complex function that we split in many let's say in math, okay, A plus B parentheses plus C and so on. We can split that. We have one function and another function, let's say one on second. Okay, now we can connect and we'll see that sensor. By the way, now test, please just look at the temperature, yeah, on your phone, and you will see here a number. What is your temperature degree now on the phone? And you will see something interesting that if you, in case, please just to check the communication, just a ping, write me your temperature from your phone. Maybe somebody now is on the CS side, we will detect him. Okay, by the way, now we are building the map of the temperature in the Chisinau, or I don't know, and the country, depends on where we are. Okay, this is another application, but we can just gather information from the chat. Okay, so now let's see. When we are here, the temperature is evaluating like this, yeah, let's say. But because of a lot of noise, yeah, somewhere here we'll have something like this. Okay, and it will be even impossible to see. Okay, I'll have from here, even the evolution of the temperature is very slow. Yeah, and usually on the screen I will see also the small changes. Yeah, I will see 1 degree per hour, some changes. This is the gradient, let's say like this. Meanwhile, if you try to make an application with Arduino, you will see that your signal will be like this. Where is my pointer? Okay, it will be like this. Now, in order to avoid that, we should to introduce some functions, so some filtering functions, and some of them could be done in the electric and the hardware side. Some of them could be done more than it. Some of them can be transferred here or transferred here, depend of the cost. Yeah, there are some functions that are embedded in the sensor I buy, and I don't need to implement such function. Okay, and now depends. So when you are a full stack, let's say, developer in an embedded system, you just decide where and how and play with those functions. Where is the real implementation? I will use some hardware feature or some software feature. Will I use libraries? But libraries are spending processing time, or I can use some hardware features that are very fast, but those cost and include some risk of burning, yeah, and are not configurable, and so on. So we always, as I say, the full stack embedded system developer usually are thinking in both domains, in hardware and software. So now, of course, not only AUTOSAR as example, I have another example, robot operating system. Robot operating system, we have some, as a platform, we have the ROS master, and we define some nodes, yeah, and build some architecture with nodes. And now it's a kind of, let's say, Internet of Things related. Every node is a provider, is a publisher, and every node can be a subscriber. So a node is publishing a topic, and the second node has a callback to this one. But this is the technology, how it is implemented. But finally, we have an architecture when we have components and some interaction. How it's publishing and subscribing, we have some platform, yeah, the ROS master, let's say, that is deciding how to interconnect them. Yeah? Here we have what? Here we have basic software platform. Yeah? Here we have ROS. Okay, we'll see in other application we have, let's say, an broker that is an IoT usually. Okay, so now how we will do that and how we will proceed with how we'll practice. Okay, for practice the to have the practice session for our class, we have defined 7 laboratory work. Every laboratory work is related to one of the topic above. Yeah, and we will have some practical examples for every topic. But we have some additional recommendation. Maybe you can use involve in parallel. Let's say we'll have some boot camps or some practice session and other things, and we can somehow combine laboratory works and all the laboratory works to build, let's say, what is my point? To build and to define one project. Yeah. So in this case, all the project, of course, will go to through all phases. Yeah, but in this case, we should have some conventions. Okay, we will. Okay, of course, it's not a kind of I come with the project and I should accept it as a laboratory work, but we have to define, yes, it is accepted in case, let's say, but it's a matter of negotiation. Yeah, why? Because when you are building a project and you have, let's say, the project is requesting for you some feature, another feature. In this case, it's an integrated solution, because laboratory works usually we have 7 different applications. Yeah. So, but we will see how. Now, when we are reporting in this format. More than is, take a look here. Source code listing is just an annexes. I need to see how we are working. I need to see engineering. I need some sketches, some row schematics, some diagrams, and so on. Yeah, and take a look on this diagram and on this slide. How should be the format of an report? Okay, more than it. Let's say the last thing. We have 1 minute. Okay, now you will be enrolled on the else. And everything you need, you will see there. Where is yours? This is here. Okay, and everything is here, and even we have some video from previous. And of course, you will be enrolled in that, and everything. Our communication, let's say, will be from different channels, from Teams. Everything else will be here. The tendency, I'll put it automatically extracted from. Okay, now, thank you. This is all for today. Just the last mark I would like to have the level of understanding. And the level of, let's say, how to say, I can say directly how much you like this topic, but it's not related more about like, but okay, let's say like the topic that we discussed today. Yes, if you want to ask some questions, just you can speak it aloud.